All right, a little bit of a late start here. Okay, so there was a couple questions I had at the end of class that I wanted to go over just to make sure you guys understand what how we're doing the SVM and the learning loops. It wasn't clear how we would do it exactly. So so if you recall, we're going to do two things. We're going to tune multiple models for a lambda value, and then we're also going to tune a learning rate. And that learning rate, we're probably going to choose one time. We're going to make a nice graph so that we can see how different learning rates react. And the way we're going to do this is we're going to have, we're going to take our data and then we're going to split it. As usual, we're going to set aside a test set. And then we're going to set aside a lambda set. And that's for lambda validation. It'll work as a test set to determine which model is the best, which lambda value is the best. Then we're going to set aside a test set for tuning the ADA. And then this becomes your training data. Now, we only need to tune ADA once. So the first time when we're tuning ADA, we're going to choose some lambda. And for that lambda, we're going to try to tune ADA. And to tune ADA, we're going to do the learning loop. And then every, what we call season, which is often called an epoch, an epoch. Epoch generally means a full pass through the data, which is why we use season. Season's a kind of a non-standard term, just happens to be what they used in the book. But every season, we're going to evaluate on a test set, a validation set, for the ADA. And then we're going to graph that ADA accuracy over time. And every time we go through a season, we're going to reshuffle this whole chunk of data to get a new validation set, just to make sure that we're using all the data we can. Now, in the homework, you happen to have way more data than you need. So I think we asked for you to do 15,000 iterations total for a single model, and we have like 45,000 data points. So we're not going to go through it all anyways, so it's less important that we reshuffle. But normally you would do a reshuffle each time, just to get a little better use of your data if you don't have enough. So now you're going to, like I said, you're going to choose one lambda, and then you're going to try to tune ADA. And you'll probably start with an ADA, see how it works. You choose that sort of M and N to determine what the ADA is, what the learning rate is. And then if it looks like it's not learning, it's really jagged and not learning, you're going to reduce the learning rate. If it's not learning and it's very, very smooth, you're going to increase the learning rate. And if it's learning and it's a little bumpy, that's okay. That's what we really want. This is stochastic gradient descent. It's going to be bumpy. Sometimes you go in the wrong direction. There's nothing you can do about that. So the first thing you'll do is you'll kind of do this ADA tuning with a fixed lambda. Then after you kind of chose the ADA, you're just going to use that for all of the models and all of the lambdas. And it's just because we don't want to retune ADA all the time. It's kind of an expensive process to keep trying all of these different ADAs. Usually once you settle on a learning rate, learning rate has a lot of slack in it. Like you could be off by a factor of 2 and still do pretty well on the learning rate. So you only have to really tune the learning rate once. Then after that, just to get kind of the loops, the idea of how we're doing this. Sorry, this is a for loop. So we're going to have some for eta in, for lambda in lambda 1 to lambda n, you're going to have some outside loop. Then for each of these, you'll create model with lambda, and then for each season, let me write this, k in number of seasons, you're going to this is where you would reshuffle if you were doing forgot how to spell shuffle. Reshuffle your train set if you were doing your eta tuning. Otherwise, you wouldn't. Otherwise, if you're not doing the eta tuning, if you're not doing the eta tuning, you use this whole training set, not the lambda set. You use this one. If you're doing the eta tuning, you have to set aside that eta valuation set. So then inside of here, you're going to have a for loop. I in steps, number of steps, and this is where you're going to do your update each time. This is ui equals ui minus 1 f of u, gradient of f of u at the current u. And so that kind of gives you the idea of you'll be creating n models, some n number of models that are lambdas. Then inside of that, you'll be doing your seasons. And then inside of that, you do the really small, those updates that are really quick. Remember, those updates are super quick because we're using one example each time. They're going to be very small steps. That's where our learning rates are actually going to be pretty low. And you're taking very small steps in sort of this pseudo-random direction. So that's kind of what we're going to be doing. Does that make sense? Questions on that? Yeah. Which one are you talking about? This test set, this validation set, or this validation set? The eta, the... So you're saying, should I use this for this?
No, just use that validation set for increasing the accuracy. Instead of like every single time you reshuffle your data, you can allocate.
Yeah, so if you do that, you might get an overestimate of your final lambda value. You could do that.
I actually think that if you do the other way, you would overestimate your accuracy because you've already trained on that.
Yes, that is true. You have already trained on that example if you're doing the reshuffle all the time for the inner loop. The reason that's okay is because hopefully you've taken enough steps inside of that, in that very most inner loop, so that it sort of has forgotten a little bit about that training set, and you've moved past wherever it was in the space. That's not necessarily true. We're abusing things here. If you had enough data, you would set aside validation sets for everything. So actually, we have extra data here. You probably would set aside a test set, lambda validation set, a mu validation set. I keep calling it mu. It's eta validation set, and the inner loop, or the training set itself. You probably would do that if you have enough data. If you don't have enough data, that's where you start doing this reshuffle, and you play a game that you're going to be overestimating. But for ADA, you don't care too much if you're overestimating, because you're just looking at trends. And that's why it's okay. I mean, it's a good question. What would happen if you tested on the lambda validation set? Probably not much, because it depends on if you, here's the thing. If you select a model, or if you select a lambda and then figure out your eta, and then once you figure out your eta, you using that, if you use the lambda validation set, and then you figured out your eta, and then you reshuffled, what you don't want to do is give the lambda you chose an advantage because you chose a learning rate based on optimizing that lambda validation set. That would give an advantage to that particular lambda that you, now it still kind of has an advantage, but like I said, there's a lot of slack in the eta, so it's okay. But if you use that validation set, I think you'd give a little advantage to that particular lambda. So this stuff gets a little complicated to think about the right way to do it. The right way is to always never reuse your validation sets if you can avoid it. Always split a new one off. If you have enough data, do that. If you don't, then we have to start playing games and do this kind of where we might be abusing it. But you're always better off having a separate validation set for every decision you have to make. So if you have to make a learning rate decision, you should have your own validation set. If you have to make a lambda decision, you should have your own validation set. Okay. Yep.
Why not do the other method, which is just like shuffle the data and you take the training in batches without replacement?
Yeah, so in practice, that's what you would do. You usually walk your data sequentially, possibly randomizing after you go through all the data. No reason. Probably no reason. From a practical perspective, you usually do walk sequentially because when you have a lot of data, it's actually, you probably won't have it in memory, so you'd probably be streaming it from disk. And if you're streaming it from disk, you're probably streaming it sequentially. You still want some randomness, so often you'll split your data into, if you have a training set, you'll split it into, say, 100 parts. And then you'll randomly select a piece of it to walk sequentially through. And then you choose another random piece of it. And so you'll add some randomization that way. The key is you do want some randomization in there, because if there's some, especially with small data sets, if there's some, just by chance, some chunk of data that leads you in a bad direction for a while, you want to make sure that you're jumping around and getting things out of order so you don't get, you don't have that happen. Often your data isn't actually IID just because of the way you collect it. It'll be like if you're doing a web page something, often you'll look at user behavior, and that user behavior will come in a block, say all the videos that somebody clicked on or didn't click on. So you have to be a little careful for those reasons. But from a practical point of view, usually you will do a lot of sequential walks of this stuff because you just can't fit it all in memory. Like I said, YouTube, where I worked before, we trained on 2.5 billion examples a day. So it took us, hours to walk through that. And it was just, you can't do it at that kind of scale. So, all right, any other questions? Cool. All right. Now we're going to jump back into high-dimensional data. This is the sheet we had yesterday, so you don't have to take notes if you don't want to. Just to recap, We're going to write our data sets with those little brackets. That's going to say it's a data set. It's going to be composed of a bunch of examples, which are, we're only going to consider real valued vectors here. We're not going to consider discrete values and things like that. From that, we can calculate a couple things. We can calculate a mean vector, which is just the set of means where you add up all of the, you take the mean of each of the different components. You'll get a vector with each of the means. That's pretty straightforward. Then we talked about just how to calculate the covariance of something. If you have two sets of floats, you could calculate the covariance pretty easily. From that, we talked a little bit about correlation, which is just correlation is just going to be covariance that's been normalized by the variance of the individual sets that you're taking the covariance of, and that will get you a value between -1 and 1. I see some of you writing furiously. Hopefully, I guess if you didn't come to class the other day, you might not have seen this. Okay, cool. Okay, so we talked really briefly about what correlation looks like. A correlation of -1 means that correlation sort of talks about, on average, when one example, a component of one example is above their mean, the other one will be above the mean. And on average, when it's below the mean, the other value will be below the mean. So essentially, it means that if you have a positive covariance, they move together. If you have a negative covariance, they move opposite. And if you had no covariance, you're going to get something like this, which they hopefully won't move at all together. They'll be completely random or no linear relationship between the different components. Then we started talking about, we just defined how we lay out the components, and then we started talking about the covariance matrix. And the covariance matrix is just the covariance of all the components with all the pairs of components. So the covariance of component 1 with component 2, component 1 with component 3. And we use this formula. Notice that this is an outer product, not an inner product. So this, the transpose is out here. So you end up getting a square matrix out of that. The square matrix is along the diagonal. This will be the covariance between the component with itself, which is just the variance. And off the diagonal, you will have, like right here, you would have the covariance of this component and this component. And then the covariance is the same across the diagonal, because the covariance of component R with component S is the same as the covariance of S with R. So you get some extra information here. Okay, so that's where we left it. Any questions on that? Pretty straightforward covariance stuff, just written out in matrix formulation. Okay, so now we're going to talk about just some definitions. Symmetric matrix. The covariance matrix is what's called a symmetric matrix. And again, that's just something where it is the same across that diagonal. It is a positive semi-definite matrix. And that's actually important. The definition of a matrix that's positive semi-definite definite is pos semi-definite. Can't write today for some reason. If for all u vectors u, u transpose the matrix u is greater than or equal to 0. So this is kind of a weird definition. Okay. I didn't label my notes very well. So what we have to look at is what we want to do is prove that the covariance matrix is positive semi-definite. So the proof for that, this is a proof. As we get farther into class here, we're going to have more math, unfortunately. So if we look at U transpose 1 over n of the sum of xi minus the mean of x, got to put a parenthesis, and then a copy of that. That's the definition. This is the definition of the covariance matrix that we just talked about. So we got to prove that this is greater than or equal to 0. We can easily push the u's inside of the sums. So you get U transpose, and then you get your, and I got to prove that that's greater than 0. And then this, these two numbers are the same thing. Oh, there's a transpose around that. Missed it. Oh no, there's not a transpose around that. I lied. These two numbers are going to be the same because they're dot products. So the dot products are going to be the same. Dot products of the these are vectors. So a dot product of the vectors is going to result in two scalars, and they're going to be the same scalar. So then, if they're the same scalar, now we have a sum of squares, and sum of squares are always positive by definition. They have to be because they can either be they're greater than or equal to 0, because if you square any number, you're going to get a positive number. So that's the proof of it being semi-definite. Now let's look at what U really means here. See how many people are still writing. All right, hopefully everybody got that. So if we have a U and we have a semi-definite matrix, what we're going to be able to find, or we can look at it geometrically, and that's sort of the interesting thing here. So we can take an example. So this is just some example out in the space. And the U's are going to be perpendicular. Sorry, I missed a point. If this is I missed a point in my notes. Sorry. If the matrix is equal to 0, if U matrix U is equal to 0, we can talk about geometrically what that means. If it's equal to 0, then these dot products have to be equal to 0. And that means they're going to be perpendicular. And so for the whole set, you're going to get a system that looks like this. For any given data point, you're going to have a U that's perpendicular. And what's more, you're going to have all of the data points along this axis. So there might be x3. It's all going to fall along that. So what that means is that the covariance matrix is somehow rank deficient. And if it's rank deficient, that means we can take it and we can reduce the dimension of it. It's basically, this is saying that if your covariance matrix is just comes out to if that comes out to 0, then the data is lying in some sort of subspace of the high dimensional space. So this is what it looks like in a two-dimensional thing. We can try to draw 3 dimensions. It's a little harder, but again, you're going to have some x1. You'll have to choose a u that is perpendicular to that. And then everyone is going to be either, if it's in the same, if it's linear, if x1 and x2 are linear with each other, they'll be like that. But other x's can lie in sort of a plane that's all perpendicular to u. It's kind of hard to draw here, but all of the x's are lying in some subspace. Basically a plane when we're looking at a 3D representation, and all of them are perpendicular to u. Does that make sense? Okay. And this is just really saying that there is an obvious subspace that we could find where the data is sitting. If we just do a transformation, we could extract that subspace and figure it out. And then rotate the data into a lower dimension. All right. Okay, now we're going to talk a little bit about transforming data. So I'm going to switch over to this. Okay, so if we want to transform data, we're going to do usually 2 transforms. Let me zoom that in a little bit. The first transform that we're going to do, now the goal of all these transforms is going to be to reduce the dimensionality of the data somehow, usually by dropping components in some rotated subspace. So what we're going to do is we're going to start with our original data right here, and we're going to translate it so that it has basically 0 mean. So we could just calculate the mean of the data and subtract that mean away, and that's the equivalent of translating it. So this data would end up looking like that. Then the next step we're going to do is rotate the data. So we're going to choose some rotation matrix. We're going to multiply that 0 mean data cloud by that rotational matrix. So we'll go from this 0 mean cloud of points into this sort of arrangement. And that arrangement, we're going to choose that rotation so that we have covariances of 0. So the components in this new subspace, new space, it's not really a subspace yet, are going to be 0 mean, are going to be 0 covariance with each other. And you can see that here. There's no covariance in this particular thing. And then the next step we're going to do, which I think we have a picture down here. I apologize. I thought that picture was right there. It may not be. Ah, there it is. The next step we're going to do is we're going to take that, in that new space, the rotated space, we're going to choose some number of components, and we're going to zero them out. And we're going to choose the components that have the least amount of variance. And if we do that, we're going to get something like this, where it's now embedded along a line on a single axis. And we might choose multiple, we might retain multiple components. So if we have some high dimensional D space, maybe we choose, I'm trying to think of what I think we said S in the book is the number of components we're going to retain. And the rest of them we're going to zero out. So this is going to result in a much lower dimensional data set, depending on how much you zero out. And then what you're going to do is you're going to undo the whole thing. You're going to re-rotate back into the original data, rotation of the data. You're going to move it back by undoing the translation, and now you have this subspace that is shown in the original coordinate system. And you can kind of look at it and view it in a lower dimensional data, the lower dimensional space, and kind of, see how the data is arranged in that low dimensional space. So this is typically, we're going to do this in a couple different ways. The way that we're going to do it first, this exact method I talked about here, is called principal component analysis. So let me look, trying to figure out where we talked about these particular graphs. Okay, so unfortunately let me go find the original here. Okay, here we go. This is the height weight data set. As you can see, it sort of looks like maybe there's some low dimensional embedding of the data in this high dimensional space. Now this isn't a particularly high dimensional space, but there's actually in this particular data set there was 10 dimensions. We're only showing the 4 that are the most obvious of this in this particular graph. But you can see kind of because you have a bunch of these sort of thin blobs, and that is kind of a technical term, oddly enough. You can kind of guess that this is a low-dimensional data set sort of hiding in that high-dimensional space. So let's go and zoom forward to the principal components again. Here's that same data space after we've done the translation and the rotation to eliminate the covariance. So now you can see that there's no covariance in these graphs. Now you can't talk about what the different dimensions are. You don't know what the features are anymore because they're in this other space. They're no longer height and weight and adiposity. They're something else. But you can come along and we can project down, maybe we project down dimension 4 and, I don't know, maybe dimension 3. I can't remember which ones this book actually does, but we will just eliminate those dimensions. Then we'll take this, rotate it back, translate it back, and then we can look at this data set. Before we do that, there is a point we want to make. This is the same thing as above, except we zoomed in a little bit. So we took all the graphs and we expanded them so you can see a little structure. You can always take, just by scaling your size, you can always make data look like it has 0 variance. So that's like the scaling of the individual components with respect to each other actually does matter because variance, if you just take the data and you put it on a different scale, it's going to increase the variance or decrease the variance. But we came along and we actually just resized these graphs so that you can see a little closer what's going on. Now, you can see that probably with direction 4 and direction 2 here, this graph, there's not a whole lot of structure. It's pretty much a flat blob in that direction 4 space. However, you do see some structure. I mean, definitely there's some structure in the direction 2 versus direction 1. And in direction 2 versus direction 3, you know, these first 3 dimensions definitely have some form to them. So there's some variance in there of all the different components. This guy, direction 4, you can see it kind of doesn't have a whole lot of variance. That would be the component we'd probably get rid of. However, you do see that there is kind of this banana shape. That's hinting there is a little bit of structure in there that if we project down and get rid of that structure, you know, get rid of that dimension, you're going to lose a little bit of that structure. So you got to be careful sometimes. You will, projecting down will always lose some structure probably. The key is that you generally want to lose as little as possible. So we're going to choose those low variance things. I would say this guy has more. So I would say these guys probably have more variance that is important. But the banana structure, yeah, there might be something going on there that's actually important. But I don't know. I mean, certainly there's something going on there. The key here is that there isn't any, the covariance on these are 0, but because there's structure there, you could probably guess that covariance measures linear changes with each other, and so there's a nonlinear relationship here among these variables, and that probably might be important. It all depends on, you know, the scaling of that variance. So maybe this is there's something here, but we don't really care. That's very possible. As we care about the second ones. Again, this is all the whole issue with different things being scaled different ways and sort of arbitrarily being able to move the variances. That's a big flaw with PCA or any of these transformations where we're going to try to drop some dimensions. You got to be careful with that in anything you do. A lot of our data, though, that we're going to work with will have the same scaling. So, like, we'll work with images, and if you look at the variances of pixels, they're all pixels. They all vary from 0 to 255, you know, in value, or 0 to 1, depending on how you look at it. And in that case, then you don't have to worry about the scaling. All right, any other questions? All right, cool. So there's one more thing you should look at here that you should notice on these particular graphs. The numbered points are odd points. They don't sit on sort of the manifold along with the other data. These are definite outliers. So we know that there's at least probably 5 points in this data set that are just crazy outliers. And outliers just cause havoc with many machine learning techniques. So we might come along and actually eliminate those outliers. Now, it may be that those outliers are informative in some way, so we have to be a little bit careful, but it's often important to get rid of those just to make sure that we're not sort of over-specializing to these outliers. And we're going to see that later on, how outliers just kill us in some of our learning techniques. So I think he has one more. Okay. So he projects down to 2 dimensions, so he got rid of 2 dimensions. Then we rotate back, translate it, and we get back to this. So now we've eliminated some dimensions. This is a 2-dimensional space that we've rotated so that we can look at it in the different original features. And you actually see that most of them actually have very little variance along any of the axes, except for weight and age, which are the two pretty important ones. Now, there's still some covariance here between, say, adiposity and weight. They're measuring very similar things. And you can just think, height and weight, there's going to be a definite relationship. People who are taller, on average, weigh more. If they didn't, we'd have a lot of weird-looking people. Let's see. You wouldn't expect age and height to vary very much, or to have any covariance, really. The exception of that is, this data set doesn't have kids in it, so we don't have to worry about that, the oddity of kids, growing up and their height changing rapidly. It looks like it might actually drop a little bit with older people. I'm not sure if that's an effect, a social effect of, people are just taller nowadays. You actually have to watch for that sort of thing. People are, on average, taller than they were 50 years ago. I don't think I don't know if it's actually a truism that people shrink as they get older. You always sort of think of your old grandma as being really small, but it might just be that, she never was all that tall to start with. All right, anyways. Okay, so let's look at the math. So we're going to take a couple of steps to do these translations. So we're going to start with our data set. Let me switch back over. We're going to start with our data set. Again, this is just going to be some set of the examples. The first thing we're going to do is we're going to create a new data set. Not sure why I can't draw brackets. I'm not very good at art for some reason. The new data set M is going to be some transformation times the ith new vector is going to be some transformation times a, times x plus b. And we're going to choose. First, let's talk about the mean of this data set. The mean of the data set x is going to be equal to a mean of x plus b. And the covariance, the covmat, so the whole matrix, is going to be equal to the A transformation times the original covmat of x times A transpose. So now let's, sorry, I thought we did this in 2 steps later on. I'm a little surprised we did it in 1 step. Now let's talk about a little bit of linear algebra. So this is just some linear algebra. If we have a symmetric matrix, and we have some vector, and you take it times some lambda, which is a scalar, and you get back the same vector, if this is symmetric, this is a scalar. And this is called an eigenvector. And the scalars are actually called eigenvalues. So these eigenvalues are interesting. They're the if you think of this S as a rotation, because that's what symmetric matrices, symmetric matrices under certain conditions you can think of as a rotation. Actually, you don't have to think about it in that case. I'm jumping forward. The U's are actually the vectors that after that transformation, they've been resized, but they point in the same direction. So if you think about just two-dimensionally, if you have a vector, some vector in this space, let's just draw it like that, and you apply S, you're going to get some new vector. So if this is X, this could be SX. You have rotated it and rescaled it possibly. That's just what S is going to do to it. However, there are a set of vectors in here called the eigenvectors, where the U is equal to SU. And that just means the U vectors don't change direction when you apply this, this transformation. They always point in the same direction. Now, they might change length due to that transformation, but they're not going to change direction. And that's going to be the important thing about this. There's a couple things we're going to enforce here. We're going to just by, you could calculate these eigenvectors in a lot of different ways. You can arbitrarily scale them. If you double the size of this, you could half the size of the lambda, and that would still work out. So we're going to just enforce by default that these are actually unit vectors. And that'll allow us to compare the eigenvectors and eigenvalues with each other, because they'll all be on the same scale. So if you get an eigenvector that isn't a unit vector, you can just rescale it. The other thing that we have to care about, you're going to have multiple eigenvectors here. You'll have an eigenvector for each dimension. Now, possibly some of the eigenvalues might be 0, but we'll ignore that. They're generally not, even in a high-dimensional space, and even if we think that we're really looking at a low-dimensional object, generally the eigenvectors won't be 0. Sorry, the eigenvalues won't be 0. So we're just going to ignore the fact that the eigenvalues are sometimes 0. Now, the interesting thing is we can put together a U matrix that consists of all of these individual eigenvectors. And there should be n of them. Sorry, I'm going to use d here because this is the dimension of the space. There should be d of them, and there will be associated eigenvalues for each one of them. And if we did that, we can rewrite S U. This is just a rewriting of this original equation. Just to make the math work out correctly, we put the lambda on this side. And that's the same statement, just written in matrix formula with a square matrix. That was what you're looking for? Okay, cool. this guy is the eigenvalues. And it is diagonal. And just by convention, we order by magnitude. Well, they're scalars, so size of eigenvalues. So we just put the big ones at top. We put the big ones up in the top corner. We put the smallest ones in the bottom corner, and so they're just in order. And that just makes sure that we can always look at the top when we do some projections later on. We don't have to search through the eigenvalues to find the smallest ones. And the other thing that is important is that this all the eigenvalues are actually I forgot the term, perpendicular to each other. That's not the correct term, but the orthogonal to each other. Jeez. So we end up with a situation where U transpose times U is equal to I, where I is the identity matrix. All ones along the diagonal and zeros elsewhere. So this matrix then is called orthonormal. And again, if we can just prove this really quickly or show this really quickly, if things are orthogonal, then that means that a given eigenvector times another eigenvector is going to be equal to 0 for anything I not equal to j. And that's just because they're all orthogonal. So the angle between them is going to be perpendicular. Unless you're raising the ceiling there. And then it'll be, because these are unit vectors, just by definition of how we scale them, the diagonal will be 1. And the important thing here, the thing that for all that math, the thing that we really care about is that orthonormal matrices are rotations in high dimensions. They're just rotations of a space. They aren't rescalings of a space. And that's going to be important because when we apply one of these, we don't want the space to be scaled to something different. So an orthonormal matrix is basically a rotation in a high-dimensional space. And what does that mean, that it's a rotation in a high-dimensional space? So let me... Rotation... that means two things. Angles don't change, and lengths don't change. So when you apply this transformation, everything, all the original vectors they'll rotate, but any two vectors will stay in the same orientation with respect to each other. And also the lengths of the vectors that you rotate are not going to change. And we can prove this pretty easily. If you take the original vector, this was written wrong in my notes. If you take the length of, that's what I meant, the length of x This is just defined to be x transpose x. Now it's actually the square of the length, but we don't care about that. And then we define some u equals to, we're going to call it r, just to denote that it's a rotation. And we take that original x, and what we want to prove is that the length of u is the same as the length of x. So the length of u, that's a vector, is equal to, this is just substituting in the various things. We missed a transpose. Now, as we said, R transpose R, because we're orthonormal, that's going to be the identity. If that's the identity, we end up with which is equal to the length of x. So lengths don't change. That's easy enough to prove. Angles, if we have some, we have some u equal to the rotation of some x1, and we have some v equal to the rotation of x2. We want to make sure that that angle doesn't change. So we want to make sure that the angle is defined as x transpose, x transpose 1 and 2. That's what we're going to define the angle. So now we got to look at the angle of u transpose v. This is equal to r x1, wait, that's transposed, x1 transposed r, r x2, and that will be, sorry, I got a typo here, x2. That will be, again, because of the identity there, that's going to be x transpose x1 and x2. So that just means the angles don't change. So we could apply these rotations. Am I not zoomed out today? Apparently I'm just writing at the bottom of the page a lot. So we can find these, this is a rotation. And we're going to use this to rotate things like we talked about, where we take the original data set, translate to a zero mean, rotate it into a new space. There is everybody got that? I'm sure nobody's writing still. Hopefully everybody's pretty much has that. So we want to go back and we want to look at SU U lambda. The one important thing about the U transpose U equal to the identity, that implies that U transpose is equal to U inverse. So we're going to take advantage of that, and that's just by definition of inverse. Definition of inverse is that U inverse times U is equal to the identity. So we get that one kind of for free. So we can rewrite this. We can get rid of the U on that side. We end up with USU equals our set of eigenvalues. And then that translates into this. And we end up there. Okay. Sorry, I want to show something again. There it is. So remember, we were trying to apply a transformation to the covariant matrix, which is symmetrical, and the transformation transposed. We want to apply this sort of thing. And you notice that A covariant matrix, A transpose, is sort of like this. So if we can calculate this U, we can do a transformation that is U transpose just by looking how this works out. We can apply the transformation U transpose. And that's what we're going to end up doing. I'm not sure why all my stuff's out of order here today. We're going to end up applying a, here we go. I'm going to rewrite this M. I knew that was wrong. Mi is going to be equal to xi minus mean of the x data set. So this is the M data set. That's going to be our first step in our transformation. And that is going to have a mean of 0. Then the next thing we're going to do is we're going to apply the rotation. So we're going to come up with our R data set. And the transformation we want to use is UT MI. So we're going to rotate into this new space where UT is defined by this particular thing. We're going to select UT such that UT cov mat of M U. And again, the cov mat is symmetrical, so we can do that. We can find this UT and apply it, and that's going to rotate us into the new space. This guy, finding this guy, any linear algebra package will be able to do that. Whether you're in R or Python, MATLAB, they all are going to have this particular transformation to find the eigenvectors and eigenvalues. And usually it's just called like eigen something. So if you just look that up for search on the web, you're going to find a package that's going to do that. So we don't have to worry about calculating this U. We're going to just get it for free by using linear algebra package. Okay, so now we're going to do a projection, just like we said before. I'm not sure why that's always off the page today. This thing's... Okay, so now we're going to do our projection. We got it rotated into the... You have an actual question? Oh, I just figured you had it off the page. Okay. Okay, so this, where did that go? These guys. Okay. Sorry, we can call this. It's just some matrix that I had written down, but we're going to the covariance of this the covariance of the R is just going to be A covat A, where A is some matrix that we multiplied times. And then we're going to choose the A. We're going to choose, at this step, we're going to choose the A to be equal to U transpose, where U transpose is found through that. So I just did a substitution there. And the nice thing about this is that now when we calculate the cove mat of our new data set, it's actually going to be equal to that lambda. And again, the lambda, remember, has a diagonal that is non-zero, and everything else is 0. Which means that if the covariant matrix of R is diagonal, that means that we have no covariance among the different components. We have some variance along for any given component, but we have no actual covariance. So that's really the important thing about that transformation, is that we end up with a matrix that has no covariance. Now, if we were to look at, let's see, I want to keep this page because we're going to keep moving along on that page. But if we were to look at that covariance matrix, remember we set it up so the biggest were up here, the smallest were down here, and everything else was 0. If for most data sets, if we look at this, what we're often going to see is something that looks like this. So if I plot the magnitude of the lambdas, if I call this one lambda 1, which is the biggest, this one lambda d, which is the smallest, the form of this, and this is just the magnitude of it, is often going to follow something along that pattern. So it's going to have a couple very large eigenvalues, and then it's quickly going to degrade down to very, very small eigenvalues. So there's going to be a couple very large variance components, and then lots and lots of small variance near 0 components. Now that's not guaranteed. There's nothing to guarantee that that happens. But it's very common in data sets. Again, this goes back to the fact that most data sets are low dimension that are sort of hiding in the high dimension. And this is basically what that's saying, is that you quickly get these variances so that they drop down to 0. And this goes back to what we're going to do where we project. We're going to consider only the eigenvalues over on this side, and everything over here we're going to project down to 0, because it's essentially 0 anyways. If you think of something that has a 0 mean and a very small variance, that's essentially equal to 0. I mean, it's not. There's obviously some variance there, but it's very close to 0. If you were to sample from a 0 mean small variance distribution, you would get a lot of values that are very close to 0. And that's sort of the justification of coming along and just saying, okay, we're going to ignore those. So let's keep working on this particular transformation. We're going to go to a new data set. Now we are going to go to P. And PI, these are all vectors, by the way. PI is just going to be the first component up to the S component, and then we're going to eliminate those low variance vectors, or low variance, eigenvalues. So basically, we're just zeroing out all of the very low variance eigenvalues. Now we're choosing that S. Again, we choose that S. We come along, and this is the S we're going to choose. We're going to choose something so that we get rid of lots of them, but the ones that look like they're very small and unimportant. Now, depending on how low you want to go, maybe you eliminate all but 2. if you want to go and look at this data set in a 2D projection, you would only retain 2 of them. Now that's going to maybe eliminate a lot of information, but you're going to keep the most important information, hopefully. Okay. So we can ask, got just enough time to talk about this. We can ask, what is the error that we're going to incur if we do this sort of projection? So that error is going to be, we're going to take the average error because that's more interesting. And we're just going to define the average error as the square difference between those 2 things. If you think about that, for all of these first components up to S, you have they're going to be the same because you're just copying P is just copy of R up to the S component. But after that, it's going to be all 0. And if it's all 0, then the difference, the square difference, is going to be the square of RS plus 1 down to RS RD squared. But those are just the variances of the individual components. So this actually becomes the variance of RS plus 1 plus to the variance of RD. So that's going to be your error. Now, we want to minimize error when we do these transformations, obviously, but we've already chosen S, so the only thing that's remaining is the low variance components. The only thing we drop is the low variance components. So they're the low variance components, so we can kind of infer that this is going to be a very small error on average. And I think that's where I'm going to stop today, because I think the next part is going to be talking about some other stuff where we look at figures. Any questions before we go on that? Yes, this U is orthonormal. No, by definition, when we talked about this transformation, these are going to choose orthonormal vectors. All of those will be orthonormal. And that's just the way that particular formulation works, is that it will be returning a bunch of orthonormal vectors. So we don't have to do anything with them. They are orthonormal by definition. And I didn't prove that. It's actually somewhat complicated to prove, but it's true. All right, see you guys on Tuesday then. There's a homework due on Monday, just to remind you. It's an SVM homework. Hopefully you've at least looked at it. We've given you most of the framework, so it shouldn't be too hard. But people have had trouble translating the equations into the SVM before, so make sure you give yourself enough time.
I have a question.
Okay.
Regarding what you said about computing eta at the beginning,
Yeah.
and then using the same value for all lambdas.
Yeah.
Right? So we just take some random subset and compute eta that seems convenient.
Yeah.
And then we do the training with.
Then you'd start over the training and train all of
And we don't
lambdas.
touch eta anymore.
Yeah, then you leave eta normally.
And how do we, in that case, fine-tune eta? I mean, you talked about 2 parameters A and B that depends on the
Yeah.
cycles.
Yeah, so it's always the form of eta can be a bunch of different things, but the one we were talking about is just sort of this sort of formulation.
Okay.
So if you make M and N big compared to K,
Yeah.
eta will drop slowly. If you make M and N very small, eta will drop quick.
So that is completely empirical for us.
Yeah, so that's just empirical. We just you can try a couple different values to see what goes on. The other thing is the ratio from M to N will control sort of the initial value. So you can think of, if you factored this out, you could factor it into some constant times m and n k plus m and n. Conceptually, you can factor this out. It wouldn't be quite right because of the k would have to you'd have to take a c out of this bottom. But you can think of it as sort of this is your initial learning rate, and then you will sort of drop over time. So often what the people do is they do a set like, I want to start with an initial learning rate of 0.1, and then they set m and n to 1, and they use k, or they set m and m to be equal to each other, essentially, and then they set k to degrade it at the rate they want.
And very quickly, what kind of order of eta are we?
Depends on the task. In that demo I did, I think I did. I just did a fixed data. I didn't actually degrade it. I think I did 0.11 was the high end.
Okay.
I think 0.06 was sort of the sweet spot,
Kind of
and 0.001 was like the low spot. Often 0.1 is where you start, and then you sort of take orders of magnitude, or probably not orders of magnitude, but powers of 2, sort of double it, half it. That's generally how I've tuned data in the past, and it seems to work pretty good. Generally, for what it's worth, you want to go down with eta. You almost always overestimate it, and lowering it almost always helps.
So, yeah, just to be sure that we want very small values.
Yeah,
I mean,
they're
not
small.
put the eta at 1
Remember, they have to. You want them to be less than 1 almost always.
Because everything is
Because you want to scale it less than 1. I mean, just it's more of a practical concern than anything. There's no theory that says it has to be less than 1. The theory just says it has to degrade over time. So, you just have to do this empirically.
Perfect.
Okay, cool.
So I wanted, thank you.
Problem because we have already finished homework 2 and we run the auto grader.
Okay.
So we get 80 about percentage. It's not the top 10 rank. So is this
That-
matter?
No, that
It's
doesn't matter.
influence
As
on
long as you
final.
did, it depends on your random selection. There's going to be some randomness. What we do is we just chose a range.
Yeah.
We figured out what the mean value of we ran a bunch of simulations of this, and we figured out the mean and the variance, and then we just took a big range around
So
that.
we just need to take a picture of
Yeah,
our
yeah. Really, what we just want to make sure is that you're not, at an accuracy of 10%, and you're not at an accuracy of 100%,
Yeah.
because one way or the other you
Yeah.
did something wrong.
Okay.
And then we're going to look at your code basically to make sure that your loops are right, you tune things correctly. So the accuracy is like 5 points
okay.
being within this large range.
Thank
So
you.
it's really small. Yeah.
Thank you.
All right, no problem.
Hi, just have a question about the SVM homework.
Okay.
So for let's say just
That is a really nice
I tried to
two-dimensional
what you
plane.
draw. Anyways, it was not completed.
I
Anyways,
could not draw that. I tried.
Yeah, so when you do A transpose X plus B, right?
Yep.
I was a little confused in terms of dimensions of each matrix that we're going to be using in here, right? So first, X is going to be features.
Yep, that'll be your number of features.
And then that depends on how many vectors you're going to use.
Yeah, it'll depend on, it's just the number of features in the original data. So your original data, you're going to select, I believe it said to select just the continuous value features. So there's 10 of them or something. I don't remember.
Let's say 10, right?
So yeah, then X would be a column vector of size 10. A is just the same thing because it's, you can think of it, if you're trying to make a plane, you'll have one component for each X. And then B is just a scalar.
So it's going to be just same number.
Yeah. So
in this case, it will be X as a column with whatever number of features.
Yep.
And then A transpose now is going to be like that.
a row. Yeah.
You kind of dot it.
Yeah, and then you're doing dot product, and you're going to come up So you take the dot product of a row times a scalar, you end up with a row times a vector, you end up with a scalar. You add another scalar, now you have a scalar left. Then you take it times the label.
Which is
Yeah.
vector, like column vector.
Yeah. No, the label is a
This one,
scalar. The
because
label is a scalar because it's either 1 or negative 1.
Yeah, right. So this would be okay if I use just one vector.
Yeah, generally you want to use a single vector.
All right.
I mean, so the B you usually, so when we write U,
Right.
you know,
You have
U,
two of them.
often you'll create a vector that's the concatenation of X would be all the X values, and then you stick a 1 at the end. And then you, A would be, you call it U then, and it would be the A values and then the B at the very bottom. And if you work out the math, it comes out to be
okay,
exactly
because
like
you
this.
do this.
Because you do this, you know, you multiply and then add them all together.
Okay.
So yeah, that's a trick often people use. You don't have to. If you look at my code that I wrote for
So
that,
you
I
separate
just
it
did
to
them as separate because it was easy to do.
Yeah,
But
all right. I'll go with that.
yeah, it doesn't matter. In the end, you have to calculate A and B slightly differently, the adjustment. So, you know, all of the A's are going to be adjusted by the same sort of gradient formula, and then the B, because the difference, because there's no X involved, when you take the gradient of the B, it comes out to a slightly different thing. So, yep.
Yeah, that works. Thank you.
All right, no problem.
Yeah, just a couple questions about what we went over. So
Okay.
what exactly is this matrix S that we're looking at? Like, is it
Well,
just
this
arbitrary-
this formulation is just a general linear algebra statement.
Yeah.
And then we can find that U, given a symmetric, it actually has to be a symmetric positive definite matrix. And if you have that, you can calculate this U just using a linear algebra package. And that U has all of the properties that I talked about, orthonormal.
So it's the eigenvector.
Yeah, it's
right?
the set of eigenvectors.
Okay, like, how do you determine what S is when you're actually doing this?
Okay, so when you actually do it, when we started talking about this formula, the S is going to be just the covariant matrix of M. There was an M in there, which was the zero mean. Yeah, so the covariance of M is equal to some U, but you're just going to use the covariance of M to calculate that you want to use a zero. Okay, so this M, if you remember, I rewrote it later on so that it didn't have.
This, right?
Yeah, it's this. So we didn't change the covariance matrix here. So you're going to use the covariance matrix of M, which is the same as the covariance matrix of X. So you're going to end up calculating this through the linear algebra package, where you take, this is essentially your S, and then you'll get back a U transpose, and that's what we're going to apply to do this. Where'd the R step go? The R, you're going to take the U transpose M that was calculated by using the covariance matrix of the original X. Using that S, using a linear algebra package to get the eigenvectors.
So you do this, you have R is just a set of all.
It's not, sorry, it's the set of all vectors, which are basically take the zero mean vectors and apply this rotation. Remember, the U is a rotation. So we just rotated them all, so they now have zero covariance.
What is this used for? Like, what's the significance of all this stuff?
So this is called, oddly enough, I skipped this, and I didn't mention it. I mentioned it early in the talk, but it's just it's called, we'll end up with something called principal component analysis, which is just sort of the name of this procedure. And we're gonna those eigenvectors are gonna become what are called principal components, which just is going to mean that we're going to be able to add up. Basically, if you take those